it was what was the name of the workshop before that? Yeah, yeah, we merged actually several workshops together. Yeah, but this is actually the second Sparse workshop, and the first talk is going to be by Saman. I don't need to present him, so here we go. Should I switch back?
We want to welcome everybody, and so I guess this is a part when you have workshops very far from where everybody is, it gets hard to travel. But I think we have a really good attendance, so I think we are going to have a great time because this workshop is bringing a lot of different people who have been thinking about the same problem. And also, I feel like with machine learning, sparsity getting very close to becoming a huge big thing. So I think we are in for a cusp of something, and to bring that community together to talk about that will be great. Okay, so this PLDI, my job seemed to be the only person who got the visa or whatever to come, so I give other people's talks. So Jeon is actually from South Korea, but he decided not to come. So I'm giving his talk. Okay, so part of this is it's great that everybody has been talking about sparsity. There's a lot of work in here. But how close are we to real? How close are we going to get performance? So if you look at kernels, sparsity is not just this one thing. There's a mix of kernel. Oops, what happened? Sorry. For some reason That's not the place to live in. So if you look at that space, there are three ways to looking at it. You can everything hand write things, and that's great. You can get really good performance, and that's what all you experts will do. Or you can limit to basically sparse tensor compilers, and you do sparse parts well, but pay the cost of mixed and dense in here. Or you can use dense compilers where you will do the dense stuff well, but not sparse. So in this talk, what we are trying to do is we want to add more sparsity support to the dense compilers and use them. So can we leverage these dense compilers in there? That has a lot of research and work has gone into. And we can code Gen for very fast kernels in here. But it doesn't support sparse formats. So the first thing is, can we reinterpret the sparse format as multiple dense arrays? Because in fact, that's how sparsity is stored, as multiple dense arrays. So what you can do is you can take a dense compiler in here. Can you do something before dense that takes the sparse code and convert it to fit into dense computing? So here's a very simple example, SPMM, using this sparse kernel in here. And of course, this is too abstract. You don't know what it is. On the other hand, the sparse kernel can be represented using many different representations, CO, ELL, and CSR. And if you use something like CO format, you have three arrays, and here's the computation you go through with the arrays. You will go get this, what index you're working on right now, dense ones, and then do the computation. And you can write it using einsums that actually deal with indirection. So instead of einsum doing directly, you can use indirection in einsum. So this computation, basically this MK val, these are indirect stuff, you can directly inline them into the einsum, and you can say do einsum here. So you can actually write this as an indirect einsum equation. So if I have indirection and einsum, voila, I got the same computation. And this is that a CO with indirect einsum. And if you have ELL format, again, some crazy looking einsums, but you can express that as einsum that directly do indirection. So little bit of a side talk here, that's great. Now we can write our sparse computation using indirect einsum. But we have dealt with formats here. So we can categorize formats into two types. There are fixed length formats, something like CO format, where loop bounds are fixed. And there are other formats that are variable blocks. There are data dependent loops in here. The thing about that is dense tensors don't know anything about this. If you look at fixed length formats, indirect einsum cannot express variables in these loops. Dense compiler are used to this. They know how to do compile that in that. And supporting variable length is not that easy. So what we have figured out is, can we come up with good fixed length formats that we can use to basically get the dense compilers work? And we came up with two different formats. So if you look at format in here, you have two extremes. CO, very compact in there, and ELL format where you have bunch of non-zero zero values you pad in here. Can you do something in the middle? Group CO says, look, I don't have to have either entire, oops, what happened? Okay, I lost. Okay, good, back in here. Either I have to have the entire row or nothing. Might not be the resting. So here you can have small blocks in there, fixed size blocks. If you have the blocks, so your rows can be computed with multiple blocks. So there could be multiple blocks in the row, and this is group size of 2. And so if you look at what you have to do, there are 4 different things you can choose from. What axis to block, block size, what axis to group, and group size. There are 4 things you want to choose in here. CO format says block size 1, there's no grouping in here. You're doing grouping of the size of the rank in here. The block CO format says you are doing both, you are doing some blocking with different block sizes in here, but group size 1. And the group block group CO, you can have a combination of both. So you can choose that depending on your data and get your interesting format in here. So if you look at the system overview in here, what you do is you get this indirect einsum in here, And we won't use PyTorch and Torch compiler to do that. And this is very easy, nice compiler. They have all those features like auto differentiation, generate really fast code using, you can use that using Triton. But there's one problem. PyTorch compiler can normally fuse things together. But they're very smart because they have handwritten code for matrix multiply. So if you look at matrix, anything looking like matrix multiply, they don't fuse. They directly generate code. So matrix multiply get generated as a gather, compute, scatter operation. And then basically do a separate gather, separate compute, separate scatter. So that doesn't work that well in here. They don't fuse matrix multiply and in there. So because they think their handwritten code is better, and people only want to do matrix multiply. So that's why you're going to end up in here. This handwritten matrix multiply call and scatter and gather. What we had done is we have hacked the Triton compiler to not directly generate handwritten this matrix multiply do that. Can we actually generate the code in here? So what we have done is we can actually generate a fuse matrix multiply, go down and directly call the tensor core to basically do that. And in fact, even if you do simple matrix multiply, we get similar speed up as the handwritten code. So let me finish by doing a couple of evaluations. So these are all run on RTX 3090, and we use the appropriate fixed length format. So the interesting thing is, for all these kernels out there, structured sparse matrix, unstructured, tensor product, sparse convolution, jagged matrix multiply, there are libraries that just do that. Oh, that's the main thing in there. And those libraries, the line of code to do that is large, from few hundred to few thousand. Neat thing about doing it using this indirect line sum is everything is single line. Okay, so you can take a 2,000 lines of code and write it in a single line. That's really, really cool because you are doing the indirect line sum. And performance is not that bad also. So only unstructured SPMM we are a little bit slow. Other stuff we are actually beating these hundreds of lines of handwritten code in there. So significantly less code, much better performance. So if you do structured SPMM, there's a blocks in here. Blocks is sparse, rest of them are dense in here. So that's how you look at it. You have 2 by 2 blocks in a sparse matrix. Look at that. So if you want to do this, the first thing you have to do is choose the right format. CO, you are 100x slower. If you do CO and group, you are about 2014x, and CO and block, you are 6x. CO, group and block, you are about 5x. And then if I actually get the compiler to generate this fuse code, you suddenly get, I think, about 4x faster than the handwritten code. So part of this is trying to get sparsity on the hands of people who are using dense. Something like Taco and Finch and a lot of other systems are going for full sparsity, all the sparsity features, bells and whistles in there. But I think people in machine learning, they are not looking for bells and whistles yet. They want to do few things very, very, very good. And they want to also make that integrated into their existing system. And this is what this is able to do. What's this able to do? This is able to do is treat the dense part as it is, keep the full performance that you can get. But if you have one or two sparse things, I can incorporate that into the entire system without losing the performance of the dense, and also get fairly good performance for sparse. In the same tool chain, things like machine learning community is familiar with. So we don't have to ask them to go do something new. They are still in PyTorch tool chain. They are doing exactly what they do. But now with few things, they can start playing with sparsity and get good performance sparsity. Okay, let me stop here. I guess we have questions at the end in the panel.
can go for one question.
We should wait for the panel, right? This is because we should get the talks too.
Yeah, sure.
That's easy.
So
Okay, I need to take the mic out.
Mic is on. Oh, okay. Yeah, thank you. And let me turn my slides. Let's see. Okay, great. Is this one? Okay, sorry. Yeah, no problem. Okay, great. Yeah.
okay, our next speaker is Jia Lee, who is an assistant professor at North Carolina State University, and he's going to talk about intelligent photo tuning for high performance sparse.
Yeah, thank you for the introduction. And thank you for the opportunity to present our recent work here. And I'm a little bit nervous, yeah, because I'm kind of recovering from the hurricane from the south part of China. And yeah, it's not a big deal for me, so it's just a flight. Yeah, but also nervous, like if I follow up the Saman's accreditation first, and I'm glad to see people here. And I think I'm maybe the person like kind of like kind of in the middle of the automatic performance tuning, performance optimization, and the compiler. So not too much into the compiler, but more on the high performance optimization part. So yeah, so good morning everyone, and let's start the talk. So yeah, this work is more about talking about the how to do the better like auto tuning. So we explore a different approach. So could be an interesting one, so let's see. And this work is collaborated with some researchers at the University of Chinese Academy of Science. All right, so let's give some motivation. So first, I'm using the sparse matrix vector multiplication here as a prototype example. So kind of, yeah, so Saman's talk used the SPMM, so here we use SPMV. But they are both like the vector part for the my vector is also dense and similar to the SPMM kernel. So we are using SPMV is because the SPMV kind of I got explored a lot extensively over like the past decades, more than 1 decade. So like that. So this work is mostly based on the people's performance optimization history and discoveries before, and then we collect the different optimization to explore a different auto tuning technology for that. So here the first motivation is that most SPMV auto tuners by far relies on the predefined templates, which will limit that performance potential a little bit. So here, what we mean here, we give two examples here. So one category is a format selector. So as people may be already familiar with that, so see, where is my cursor? There is my mouse. Okay, here. Yeah. So as people are already familiar with that, so the format selector, which means as in Saman's talk, we already introduced what is CO format, what is ELL format, and more complicated format, groups format as well. So we haven't explored, so a lot of complicated formats, but we covered like a lot of handwritten formats by far. So now, as you see here, so as a format selector, which means that you have the existing different formats, and then by choosing this format, the basic idea is that you're choosing between this format to get the optimal performance. So then, which means that your output will be one of these formats. So now given, like, for example, 3 formats here, so CO, EL, CSR, and then your output will be, well, I think for the particular input matrix, we can choose when the CSR format is the best for this particular matrix. Or we think, okay, for another sparse matrix, we think the CO format is the best. So then you kind of, that's your output. And after you've chosen your format, doesn't matter which kind of the technologies you are using, or using some people from the previous research, like some people using the offline plus online model, like by using decision tree or by using the convolutional neural network, also different models people are using. But then, so afterwards, you choose a particular format, and then accordingly, you use that format to your application. So that means like you have a particular kernel, right? So the code for the format. So this is the first category. We call it format selectors, which has we only put 2 representatives, which is smart and wise, but there are more work than that actually. So for the second category, we choose a representative as a compiler technology-based autotuners, which goes more finer granularity than the format selectors. We choose the representative Waco and Taco, so from Saman's team. For the compiler technology-based autotuners, more focus on the primitives. So it is finer granularity, and we have more information to that. And also, so for each primitive, you can notice that there is a red line here. So for the red line, which means we need to connect the primitives together to form a code. So after as the output, this is a code generated output. We got the FPMV code as the output by connecting these primitives. So this is 2 classical approaches. And so these approaches were very successful, and they got good performance, very well performance. And then, so another motivation we want to say is that, we'll go back a little bit for that. Another motivation we say that if we want to pursue a particular high performance for a particular kernel actually, so for this example is SPMV kernel, then so actually there are more space, for larger search space there, so which will significantly increase the search overhead. So come back a little bit for these 2 categories, that because of we have limited formats here, so that it limits the search space. So then the search space is not too bad. But actually, if you consider like when you search over the different, when you given of matrix, it's still it's still a non-trivial overhead, but it is manageable. Well, second category also like that. So if we have a compiler technology-based autotuners, and it's also manageable by Waco and Taco. So we are thinking that actually behind that there are more space than larger search space than that. But the search space comes from, for a particular sparse matrix or a particular sparse kernel, there is already a vast search space. So that's why we only focus on a particular kernel as this work. A good example, a representative for this direction is our previous work, which is AlphaSparse. So by using AlphaSparse, we try to split one format into different actions. So then the actions kind of means that you are modifying this format along with the time. So like we do a compress. So we compress the matrix first, and then so after that we do another operation, and then we change this format. So the format goes along according to the operator. All right, so by using this format, we can see a more like, we can release the search space, so which is vast. But which showing in this figure that we have different operations here. So the operations now we are collecting from all the like handwritten SPMV code by far. So the different operations, then you can see the red line. So we choose one of the operations for each level. So then they could be the repeated different, it could be different operations, it could be the same group of operations. And then we keep changing this matrix until the end that we found an optimal one. So then we got a path from the operation 1, 2, 3, so like that. So which is two-dimensional, that's why we have a footnote and both a supernote there. So that's the point that why we have the vast search space. And then on this vast search space, Sparse, the previous work, like the search overhead is very large. So we just got this approach, like we can see there is a large search space in this work, but we cannot handle how to reduce the overhead there. So this work, we propose introduce a behavior monitoring cloning concept to this one. So this concept, which the goal is we want to develop an auto-tuner delivering both high performance, SPMV performance, and efficient search. So we emphasize on to shorten the search time by, Sparse work, which is a pure offline work that we only give a mere metric, so which is mimic like how human people, how a person, what he or she will do when developing SPMV code. But so that's why we think, okay, even though it takes a lot of overhead, that's comparable because when we design SPMV code, particular code, we still need to take like hours, days, right? So that's reasonable. Well, so here we want to even shorter the efficient search. So then given an input matrix, then we want to change its state. So we propose a concept which is state corresponding to behavior cloning. And then so we have actions here. Action which is actually the same with the operators we mentioned before. So according to the actions, like the matrix keep changing. When applying each action 1, action 2, so then each time we predict the next action based on the current state. The state is not just the status or anything like, not just the input matrix, but by far the matrix we have seen after applying the previous actions. So this is the main point of this work, and we keep growing this action. So then we still see the vast space, and then so this is a table to compare between the behavior cloning used in other applications compared to introducing into SPMV auto-tuning world. So like action, it's like when you drive the car, it's like braking, accelerating, something like that. Well, corresponding to our world, it's the operator. Well, the action sequence, which means you drive from one location to another location, which means we design a program for this case. And the state, which means like when the state is camera images, you captured the current state with using the sensors cameras. While in the SPMV auto-tuning world, that we partially complete the program design, which is just a partial program by far. So this is a connection between the behavior cloning, and then this shows the actions we are using, so I'll quickly skip this. So all the actions, you can see there are references here, so these are the parameters actually, but there are a lot of references behind this action, so we collect from the research by far on SPMV particularly. So this means we have 4 categories: matrix layout, conversion, that you convert the matrix into a different matrix by compress, so on, for example, and the data mapping, which how you map to the GPU, how you map to the one thread block, one warp, one thread, so on, different levels of mapping. And then also we need a reduction algorithm. So how you do the reduction by atomic or the segmented, so different algorithm to do the reduction at which level, and kernel configuration. So totally we take 24 actions, and then so the state we are considering, which is intermediate representation. So we have the format representation and kernel representation, which corresponding format representation corresponding how you change the format accordingly. So which is corresponding to this part, the matrix metadata set actually. So you can see there are different layouts for the tensor, for matrix, and then you have the different reduction. So matrix metadata set, which are a bunch of arrays together, and it could be redundant. Some information could be kind of duplicated from each other, and some overlap with each other. That's why we want to keep this information, but it should be less than the input matrix. And then so finalize after we found the optimal IR after we applying a sequence of actions, then our output will be a final format. So we generate like the format which could be different from CO, could be different from CSR, but could be a totally new format from there. So based on the IR, which we call it, actually IR is our state. So we take the IR as a state, we take the operators as actions, which match to the behavior cloning concept. And then, so this is our framework. So the overview is that we have online phase and offline phase to reduce our overhead. So from our online phase, we take the input matrix, and we got the IR, which is the state. And then so we got also extract the state features as well based on that, because the state is still large. And then so after extracting the features, we have two models here. So action selection model, and then parameter, which according to each action, there are a bunch of parameters. So parameter prediction model. So we have two models, and then to predict the action we are going to apply. So when we predict the action, we apply it back to the state to see like how it will change the state. And after we got a good one, so according to the model, and then we append one action to the sequence. So by applying the whole sequence, you got the output optimized like SPMV program. So on, so the offline stage, which focuses on the initial stage and self-training stage. So initial stage, which is very common, but why we introduce the self-training stage is because we want to train on a lot of matrices, but if we need to label that is expensive. So we need to run extensive, because we are not just label it by the optimized format, we are label it by all the internal like state. So this is our data set actually. So by using that data set, labeling is very expensive. So we use a pre-trained model. So we separate into different stages. And then by using the initial stage, the learned model from the initial stage, we use that model here, student model, as a student model to train, to predict, learn the refine the model from the second stage, and then refine the model again and again using self-learning. So this is a concept of self-learning and teacher-student model. So then we can keep growing and keep refining this model. So in the offline phase, which the model will be used in the online phase. All right, so I think I'm running out of time, so I'll just show a little bit like speed up. So the speed up which we gain like compared to human written programs, we got speed up like could be different according to different formats, and we use compared to Sparse and different like CSR5, so on. So like could be up to 15, 12, could be up to 10. So yeah, different formats. And we compared our previous work for Sparse, and also the PTT, which means the best format selector, which we do the exhaustive search. So which means we can get speed up, compare 3 times speed up compared to PTT, which means like the format selector has its limitation on the search space, and compared to TACO as well. So then the search overhead, we reduce the search overhead per matrix, which was 10 hours in our Sparse and in the exhaustive search, and reduce it to almost like 0.3 seconds. And which then, so people can really, you don't need to worry about like how you take small time by designing the format, but just use the two. So yeah, so our model is based on tree-based model XGBoost. And we compare the accuracy, so that you can see the initial stage, the accuracy is just 70%, 75%, and then goes until the 6th stage, it goes to 96%, and 7th stage actually, so it's not increasing, so it's kind of bumping, like some metrics get better, some metrics get worse, so we stop here. So at 6th stage, we don't need a lot of stages, but each stage we have 1,000 matrices, so totally we train on 6,000 matrices, and this is some information. So the results we tested on 2 major GPUs, and we are thinking of this is future work to extend to tensors, but by 2 approaches, because tensor approach, like especially for multi-dimension, we don't have sufficient actions by far. So we need to develop by ourselves. And another big thing is the data set. We don't have sufficient data set to do that training. So that's two major challenges for us for the future. So sorry for the overtime, and thank you for the listening. Welcome for questions. Yeah.
Oh, for the microphone? We'll see. I think. Okay, yeah, sure.
Okay. Our next speaker is Kazem Cheshmi, assistant professor at McMaster University, who is going to talk about loop fusion in matrix multiplications with sparse dependence.
Thank you, Amit, for the introduction, and good morning, everyone. I'm presenting loop fusion in matrix multiplication with a sparse dependence. The work is led by my PhD student at McMaster, which I'm presenting on his behalf. The consecutive matrix multiplication, which is the focus of fusion in this work, often happens in many applications, which I listed some of them in here. Well, I'm starting with the graph neural network as an example throughout this presentation. That's why I'm explaining, I'm showing the closed form of one layer of graph neural network here. Particularly, this is a graph convolutional network. So in graph neural network, it's a type of neural network that operates on graphs. So as you can see, in one layer, we have two pair of multiplication, like multiplying matrix A with H, and then H with L, or the result of that with W, which is the weight matrix. And then this is a ReLU will be applied for each layer. So here you can see a few pair of operations, and I'm listing two of them, which is actually interesting for this presentation. One of them is we have dense matrix multiplication, which I use GEM from here on because it's pretty long, and followed by a ReLU. And then the other pair that you can see is two matrix multiplication, as you can see, A times H, and the results times W. So as you can imagine, there are lots of data exchanged between these two pair of operations, and if you want to reuse those data, the solution is fusion. We are all familiar with that. And to start explaining the idea and how the fusion helps data movement, I will start with the simple case of ReLU, GEM with ReLU. As you can see in this slide, I'm showing a pair matrix multiplication, which is shown with triply nested loop at the top, and then the ReLU operation, which is an element-wise operation, goes over the matrix and apply the ReLU in each element. So ideally, the D matrix that is created here, it's a common between them. So if you want to visualize this, the green colors here are the locations that will be accessed to compute one row of D1, which is shown with blue, and then the same row will be reused in the next operation and stored, and finally we can compute the row at the final results D. So if you want to reuse this element D, we want to fuse these two loops, as is shown on the right-hand side. Very simply, we fuse the I1 with J1, and then we have the loop on the right-hand side where the accesses to the intermediate matrix now are very close to each other. So that's going to stay in the cache, and we can reuse the cache information. Of course, there are so many other ways to fuse GEM with ReLU, but that's not the focus. This is just for illustrating the point of fusion, which actually allows us to reuse the data, in this case, in the cache. So that's actually a very nice transformation that can improve locality. What about the GEM? Let's say we have two matrix multiplication back to back, and we have this, again, V1 matrix intermediate result. We want to use them. How can we actually do that fusion? let's look at the code again. Here we have D1 shared between both of them, and if we want to follow the same approach that I just discussed, we can just simply use the outermost loop of these two operations, and we get the code on the right-hand side, and again, we are getting reuse on D. Well, that's actually reuse happens, but unfortunately the results is not correct, because the second operation after fusion will get the incomplete results from the D1, and that's why we are getting the wrong results, because in other words, we are violating some dependence after fusing these two. Let me explain this visually, so actually it becomes more clear, since I need this example throughout this representation. So here I'm showing the wrong fuse code, and again, in the first matrix multiplication, you see the green color that shows where it's access to compute one row of the intermediate matrix D1. And if we want to use that row to compute one row of the final matrix D, we need actually those red locations, which is not calculated in the first after fusing these two operations, and that's why we are getting the wrong results. So the reason for that is because of what we call dense dependence. So in order to compute one row of D, we need to compute every single row of the intermediate matrix D1, and that's what we call dense dependence. Now let's actually make our assumption a bit more realistic by assuming that matrix A is a sparse, which is the case in many applications, including the GCN that is the focus here, at least for this presentation. So here, instead of having that dense A, we have this sparse A, which some of the elements are removed, like basically because those are zeros. So now if we do the same thing again, compute the first row of D1, so we have, can we do the multiplication? Still, we can't do much with that, but if we compute the second row of the D1, basically if you compute one tile of D1, which is with size 2, and then we can use that 2 row to compute the 2 rows of D, the final matrix, correctly. And the reason for that is because we have 2 zeros in the second and those 2 columns on matrix A, and that sparsity allows us to fuse, basically to reuse this partial reuse between tiles, basically that tile D1 and a final tile D. This is what we call a sparse dependence, because for computing the 2 rows in D, we don't really need to compute all rows of the intermediate matrix. Well, the question is, well, that's a nice feature to have, but is it realistic? We indeed did this investigation to compute the reuse, the percentage of operations that share data on the y-axis, and the x-axis shows the list of switched sparse matrices sorted by density. We indeed compute the share data reuse between these two operations, let's say between GEM and SPMM, to see how much it is realistic to actually focus on this fusion. And we found that actually this property naturally exists in many of these matrices. Well, even if it doesn't, you can apply reordering, but that's, again, I don't want to talk about that in here. So with that property, we actually had motivated our work to focus and come up with a system that actually benefits from this partial fusion, and that's what we call tile fusion. So we propose tile fusion that has 2 components, compile time and runtime, and basically it starts from an input code and ensure that the dependents are not violated, and finally, though the generated compile time will be used to actually do the actual calculation. So in the compile time here, as you can see, it's starting from an annotated loops, which I will show you in a bit. We have dependence analysis that creates a DAG generation code, and then we have this tile fusion lowering, which actually combine the 2 loops. And then at runtime, once we have all this code generated, we take the sparsity pattern of that matrix, A in this case, and then we create a sparse dependence that we are interested in, and then the scheduler that we created, and finally we run that schedule in the fuse code, and we have the final results. So the code, the tile fusion prototype is implemented in Python using Numba. We implemented as a pass, as a compiler pass, which the input is 2 annotated loops with FP range, as it's shown in here. So these 2 loops are GEM and SPMM. So then, once we parse the input, create the SSA form, and then we merge these 2 code using a template, a transformation template. tile fusion lowering, I call it here, where we put these two codes, these two multiplication back to back with some basically loop bounds that are defined at runtime. So basically the reason that we have this is actually causes a conditional statement that actually we can populate at runtime to make sure that actually those iterations that actually are fusible are there. So that's basically what the tile fusion lowering is. And we will see how that T is calculated, which is pretty much the schedule. So the other component in compile time is the dependence analysis. As we discussed, there are like we cannot just do the partial fusion anywhere we want. There are certain situations that actually should be met before do that fusion. And in order to do that, we are analyzing the two code. Like we look at the shared data space here, for example, D1, and we look at the read and write instances, read and write accesses, because we want to find read after write accesses, and we want to make sure those won't be violated. So once we have these read and write accesses, we can compute the intersection of them, where it gives us where the read after write dependence at runtime, and then with that intersection, then we can generate an equivalent code to check that condition at runtime. And the code actually is shown on the top over here, which is actually a very naive code, because literally it goes over the full iteration space and check whether actually these two equations are equal. But we can do actually much better than this, and the reason for that is because we can simplify this equation over here by just simply knowing that I3 and J3 are fixed iterations, and then we have this constant n, and then we simple symbolic simplification that we use SymPy package. We can actually get this equation where you can generate this code, which gives you with, we can generate that dependence at runtime with O non-zero. So with all of this in place, we can go and see how the code will run at runtime by taking sparsity pattern and run the DAG generation, and then the tile fusion scheduler, and then finally the fuse code to compute the actual calculation. Let's start with the DAG generation phase. So DAG generation phase takes the sparsity pattern of A, as shown in here, and then we run that code that is generated based on the code analysis, and gives us this graph over here that the colored vertices, the blue vertices, show an iteration of the first loop, and the white one represent iteration of the second loop, and edges represent the dependence. For example, here we have a non-zero here in the first row, and that causes an edge dependence between iteration 2, the first loop, to the first iteration of the second loop. So having this tag, now we are ready to build our fuse schedule, and that's where we're using the tile fusion scheduler. So we have simply, that's a library call that actually takes a DAG and performs fusion, and the whole, that has two steps. I don't want to talk about that scheduler. You can look at our paper. But overall, the idea here is to create this independent workloads that actually has maximum fusion. So maximum fusion means like we are mixing this blue and white vertices as much as possible. And of course, some of them can't be fused. And that's where we have the second, we have this barrier, and we put them on the second, what we call wavefront. So with this, we have our fuse schedule, and we should pass this fuse schedule to the fuse code that we initially lowered, I showed you before. The only thing that I want to add in terms of the fuse code is that we have a bunch of fuse codes that actually kind of comes from the different combinations of these loops. So this is the closed form of the operation, A times B, and then D1 times C. You can see it as A multiply B times C, which is kind of a, could be Einstein notation for tensor compilers. We'll see that. And then here, when A is a sparse, then we have B and C are dense. Well, we have gem SPMM and SPMM gem. Those are the loops, kind of, we name it. And then if A and B are sparse, then we are fusing actually two SPMM together. So these are the possibilities for the two loops that we have studied, and we have results for them. I want to talk about the result briefly. I don't want to go over all the results we have in the paper. We use the CPU, and we also have GPU results. I'm not showing the GPU results here. The end-to-end experiment on the GCN is what I'm going to show you, but feel free to look at our paper about the suite sparse matrices we tested, and also comparing with prior work like tensor compilers and the sparse tiling and communication avoiding method, and each of them actually kind of trying to solve a similar problem. with different limitations, advantages, of course. So the end-to-end training that I want to show is the GCN that I discussed initially. So pretty much you can see the layer again here. We want to replace the operation here in this layer with just the GEM-SPMM, the fused GEM-SPMM that we created, and we compare it with the based on PyTorch geometric, PyG, to see how it works. And this is actually training because the the sparsity pattern of A will remain the same for the full batch training on the GCN in PyG. And the results actually was, you can see it in this graph. We have a bunch of graphs which are listed in that table. And the x-axis shows the ID and the y-axis shows the speed up over PyG. So we integrated both, basically our code into Python to be able to do this comparison. And as you can see, in most cases, actually, Tile Fusion performs better than PyG. So that's actually a very short presentation of this. Before actually wrapping up this, I want to briefly talk about some of the research that we are doing in SwiftWare Lab with my students, which is actually related to Sparse. So it's good to give you have that discussion here, well, because all of you are probably working on Sparse. So in the SwiftWare Lab, what we are doing, we are optimizing code and data together. So we have a pipeline of data that look at the data and compress it in lossy or lossless way. Like a lossy is pretty much when we are losing accuracy, and lossless, we can reconstruct the data without losing accuracy. So these red blocks are the works that actually, some of them I will talk about it briefly in the next few slides. And also, once we have that, we have compressed data structure from this compression, which we use it in our pipeline, in our compiler approach. With one of them you saw, the Tile Fusion. We have a number in the Sparse course as well, which again, I will talk about it briefly. I will start with the data pipeline. So this is actually a PhD work by Samira, who's led the work. We propose a new data transformation for fusing, compressing floating point data based on entropy information across different bytes. The idea here is when we are dealing with type information, different bytes have different behavior, and we can use that actually to reorder the data, retransform the data, and then we're getting a better compression ratio with the same compression tool. So that's actually for the lossless compression pipeline. We also have lossy compression methods that we use in sparsity to remove some of the elements. Here we are using you're seeing a triangular solve, a sparse lower triangular solve in the conjugate gradient solver. So we have wavefronts. We have synchronization that with the sparsification we can get rid of some of those synchronization. For example, here from 3 to 2, and then we can get performance end to end without losing the convergence. And this is again led by my PhD student Da. And then we have a normal and sparse quotient for matrix multiplication, which is actually for GPUs. Here you can see that we are doing matrix multiplication with two different schedules. The color cells show the memory locations that are accessed by each thread in the GPU. The first one is a naive one that we go over 1 down 0 and we do the multiplication. And then we do the thread coarsening on the right-hand side by doing two compiler directives, two unrolling. And then eventually you're going to get each thread we're going to do more operation, and that actually gives you a better locality without losing the load balancing. Again, this is another work led by my PhD student, Hossein El-Bakri. And here is the Tile Fusion summary. I guess because we are taking the questions at the end, I don't need to give a summary, but I will be happy to take the questions in the panel. Thank you.
You might want to carry the mic around for questions. Okay, no, I think one probably has to go for questions. I think I'll hand this mic to Yeah. I mean,
both Triton and also followed by Torch Compile has scatter gather. So the question is, they do good job in scatter gather. One thing they didn't do is if they didn't fuse it with matrix multiply. And so one thing because they thought their handwritten code for matrix multiply is so much better, so they just didn't. Whereas other places, if you have other kernels, it will fuse. So what we had to do is kind of undo that part and basically add ability to fuse into matrix multiply and actually generate matrix multiply by directly calling the tensor core dot product operation. So we basically generate the tensor core dot product operation for matrix multiply, and what that means, the scatter gather get fused into that, and that seemed to do pretty well. Yeah. Yes. Yes. Yeah. So you do indirect sum basically is going to do the gather, and then also probably do indirect sum if it is in the output will do the scatter into that. Yeah. I think the sparse polyhedral work is a very different approach there. So as far as I know, what they are doing is they are completely remapping the iteration dimensions into a completely new set of dimensions to make it into a polyhedral. So they are looking at these patterns and doing that. This is so much more simpler. You are not doing anything too complicated. And what we say is basically when you have this sparse format, they are the data is stored in dense arrays no matter what. There's no sparse storage arrays. It's everything is dense in certain ways, and some of them are indirected. So just keep, first thing is get INSUM to understand the indirection part. That is universal. Then Keon might not like it, but my part is there are a bunch of hacks you need to do to get it work on TensorFlow, because Torch Compile, sorry, Torch Compile basically doesn't deal with bunch of things. So part of that is get it fused. Other part of these dense compilers is they can't deal with loops that has data dependencies. So you need to come up with a format. So if you get those two, you can fit that square peg into the round hole of Torch Compile, and it works. And in some sense, this is very simple. By the time you do those two compromises, what you have to do is pretty simple. In fact, the changes to Torch Compile is basically we have submitted it to if it is flowing through the system, so it might be part of Torch Compile at some point soon.
Yeah, that's a good question. I didn't talk about the code size. Actually, for this work, we are not, we are literally copying the original code and put it in that templated code. So the code size will be pretty much the same as the original code size. And this is basically the specialization, or like where happens at runtime, is where actually the order of operation will change at runtime. So basically, we are keeping the order of operation and initially the same, and that actually gives us this benefit to simplify our transformation. We don't really have to do any complex code analysis, and we could just, as long as the runtime will take care of the dependence. Yes, that there is a dynamic scheduling. That's why we are creating the DAG of iteration at runtime, and that takes care of the ensuring the dependence. But if you want to basically unroll some iterations, that actually was something that we were thinking to do in the sense that when you look at the data, there are some patterns that actually frequently happens. For example, you have two non-zeros and then one non-zero, or like some order like that. That you can use those to unroll some of those initially, and unroll and fuse, of course, initially. So you don't really need much runtime. Or for some specific pattern like a banded or things that are actually very common, that's actually very simple to use this approach with hard coding and without actually using runtime. But the runtime schedule that we are using is actually also very simple, and with that simple approach, I mean, we just literally go over each tile and do O non-zero operation, and that was sufficient to get performance to move. So that's why we really didn't go much further. But that's actually totally reasonable expectation.
So in the matrix multiply, you do fusing two things. Basically, it depends if the first one finishes early, I can start the next one in here. Have you looked at something like a jagged format where the finishing happen in different points, and so basically you don't have to do that much work. You can figure out where it finishes, and then at that point you can say where I can launch the next one.
That's excellent point. So basically, we didn't look at that jagged form that you talked about. I mean, but we try to actually just keep this for any sparsity. But of course, we don't perform very well. But for example, if I know this is jagged or like a let's say banded or something. For example, for banded, you can get an excellent speed up, which we didn't actually report it here because that was very specific. But indeed, if you have that notion of describing a sparsity, a compile time that you do in Finch, for example, or something of that nature, then really the fusion can be customized to that specific pattern and gives you much better performance.
I think that can be great because you might not have to do any more analysis additional because it's already done in the format. It's there. You just have to run it. Yeah.
Well, yeah, for sure. So the reason I didn't talk about it because you just talk about reordering, then what reordering, like lots of them. But just to the simple thing that we did, when we saw the fuse ratio, what we define as fuse ratio in some matrices are very low, less than 1%, the relative matrix that we have. We reordered using RCM, and that gives us like a banded form that gives you a good compression. Of course, for graph neural network, that's not a problem because reordering the matrix, you just need to reorder the ReLU and everything should probably work as is. For linear solver, that's not the case. That's probably why we were a bit cautious about talking reordering much in this paper because we have a use case of linear solver as well. But yes, with reordering, actually, you can get a lot of nice properties that you can describe a compile time, as someone also mentioned, and then you don't really need to do. You can do a lot of this work actually at compile time. Yeah, yeah, sure.
Question for you. So the interesting thing is using machine learning to do these stages. It's really cool. So you can really reduce the search space. How do you represent the sparse tensor into the entire system? Because now the system has to understand the sparsity properties as well.
So yeah, so basically, so before, so we understand the sparsity feature by extracting the formats such as like statistics. So then we can, for example, the statistics could be the like how many non-zeros in the sparse matrix, or how many like non-zeros per row, or the statistic of the non-zeros per row, so such thing like that. And now, so we change it into another step by using states, and then the states can which is which include more information than the like extracted feature we did before. So then, so the states which is so a couple arrays like that listed, a couple arrays which handle abstract of the input matrix, and then we extract the features as well based on the arrays. So now we have like close to more than like 150 features you by extracting from the states. So then, so that's a representation for the matrix, and it can keep changing so over time. Yeah.
Are those two states known? So did you provide the features to them?
Oh, so the initially the features is provided from the input matrices. We extract the features, and afterwards, right after you apply one action, it will change changed according to the action, and it will kind of learn. So over the time, yeah, over the actions, yeah, yeah. Thank you for the good question. Yeah. Oh yeah. That's a good question, but yeah, that's not changing over time. So we are so that's brings a little bit limitation. Like we are still focused on the 100 and like for example 150 features, but that's not changing over time. So yeah, so we still extract the feature. Yeah. Hmm. Yeah. Exactly. Yeah, yeah. Not all of them are valid. So that's reduce some search space actually. So that's we already take that into the consideration in the initial stage, like when the action there is some pruning stage, that pruning steps afterwards. So when it does not make sense, we don't choose those actions. But there are I think there are around there is a number. So at least so there the combination number is pretty huge, but as we haven't so it's hard to calculate like how many of them are not valid. But we say like there are at least there are like 200 valid ones at least for each of them. So they're still like create vast search space. Yeah. Oh yeah, PTT. Yes, you got it correctly. Yeah, that's good question. PTT represents the best format selector. So format selector, which means like your search space is limited by those formats. You can only pick the best formats, even though it is the ground truth for the format, but the search space is already limited. So that's why it can outperform the formats because we can create new formats. So yeah, right, exactly. Yeah, so that's why some like for a particular sparse matrix, you may have the best format maybe not existing by far. So then we can create one like from the sparse matrix. So that's why it kind of outperform. And then that's also the reason like why we are not outperform a lot. Like it's just like 1 time to 3 times at most. So that's why some because still most of the good matrices and the good features matrix already been studied by people. So that's why most of the formats they are already covered. Yeah, yeah. So yeah, very good for the kind of in the middle part, the boundary part. Yeah, yeah. Thank you.